Today, we're diving into a principle that lets engineers find a clear signal through decades of noise, the superposition theorem. It's a really powerful way to understand the incredibly complex life of an energy well, and we're going to break down exactly how it works.
So let's start with the core problem we're trying to solve. Analyzing a well's performance over time isn't as simple as just looking at one steady number. The reality is, well, it's a lot messier.
So, picture this. You've got a well that's been producing for years, maybe decades. Its flow rate has gone up, it's gone down, maybe it was shut off completely for a while and then fired back up again. All of this history creates a really complicated, messy pressure signal. How on earth do you make any sense of that chaotic data to figure out what's really happening deep underground?
So how do we solve it? Well, the trick isn't to tackle the whole mess at once. It's to break it down into simple pieces. And that brings us to the elegant rule of superposition.
Okay, so here's the big idea. The superposition theorem basically says that the total, complex pressure change you see in a reservoir, it's nothing more than the simple sum of all the individual pressure changes that happened along the way. We can look at each and every change in flow rate as its own separate little event, analyze it, and then just add them all up.
Now you might be thinking, wait, why can we just add stuff up like this? It seems way too easy, right? Well, the reason this whole thing works is fascinating. It's because the physics that govern how fluid flows underground, the diffusivity equation, is linear. And as you can see here, in a linear system, the whole is literally the sum of its parts. If the physics were nonlinear, the parts would interact in all sorts of complex ways, and this beautifully simple trick of just adding things together, well, it just wouldn't work at all.
To make this really intuitive, let's think about ripples in a pond. When a well starts producing, it creates this pressure drop that spreads out through the reservoir. It's just like dropping a single stone into calm water and watching that first ripple expand outwards.
Okay, now, let's say the flow rate changes. That creates a second, totally new pressure event. You can think of this as dropping a second stone into the pond. It creates its own independent ripple that also starts spreading out, completely ignoring the first one.
And this is where the magic happens. That complex pattern you see on the water's surface isn't some new, indecipherable thing. It's simply the height of the first ripple added to the height of the second ripple at every single point. The total complicated effect is just the two simple ripples added together. That's superposition.
All right, so we've got this awesome idea of adding things up. Now let's see how it's actually used to untangle a well's complicated history over time.
This brings up a really fun puzzle. The math works great for modeling flow, right? For adding ripples. But how in the world do you use this principle to model the exact opposite? A well that stops flowing entirely. How do you model a ripple that just stops?
The solution is this incredibly clever mathematical trick. It's kind of genius. So follow these steps. First, a well is producing at a rate we'll just call plus Q. When it gets shut in, the model just pretends that the production continues. But, and here's the key, at the exact same moment, it adds an imaginary injection well at the exact same spot, flowing at a rate of minus Q. And what's plus Q plus minus Q? It's zero. It perfectly models a well with no flow at all.
Now this math hack has a very real physical consequence. It creates something called the inflection circle. Think of it as a moving boundary, a kind of bubble expanding from the well. Inside this circle, closer to the well, the injection effect is winning, and the pressure is actually recovering. But outside the circle, the original production ripple is still spreading, and the pressure out there continues to drop, just as if the well had never been shut in at all.
And here's the really crucial takeaway from all this. As this quote explains, because that original production signal is always there, acting as this moving baseline of pressure decline, the reservoir pressure can never, ever fully recover to what it was at the very beginning. That first ripple never truly goes away.
So, that's superposition in time. But we can use the exact same principle to map out invisible features underground. This is where we get into superposition in space.
This technique is called the method of images. And the idea here is to use these imaginary or virtual image wells to perfectly mimic the physical effect of a real boundary in the reservoir, like a fault line that completely blocks any flow.
And how this is done is just so smart. Check this out. If you want to model a no-flow barrier, like a solid wall of rock, you place an imaginary producing well on the other side of it. The combined pressure drop from your real well and this ghost well creates a pressure wall right between them, where nothing can flow across. But what if you need to model a constant pressure boundary, like a huge aquifer right next door? You do the exact opposite. You add a virtual injecting well.
Its pressure support perfectly cancels out your producer's pressure drop right at that boundary line. It's brilliant.
So let's bring this all home. We've seen how this one simple idea of adding things up is just ridiculously powerful, not just through time, but also across space.
So you've got these two powerful applications, right? On one hand, you have superposition in time, which lets us untangle a really messy, decades-long production history. And on the other, you have superposition in space, using these imaginary image wells to map the unseen geology all around a real well.
And really, that's the core takeaway here. The superposition theorem is this beautifully elegant principle that allows engineers to take a problem that looks like complete chaos, something totally unsolvable, and transform it into a straightforward series of simple additions. It truly is a case of turning chaos into simple sum.
This leaves us with a final thought. This fundamental idea of breaking down a complex system into its simplest linear parts and just adding them up is so incredibly powerful. So the question is, where else, maybe completely outside of engineering, could this way of thinking turn a seemingly impossible problem into something beautifully simple?